Hello everyone. I am Dr. Amy Sabita, working as Assistant Professor in Department of Chemistry, Sadakatullappa College, Tirunelveli, Tamil Nadu, India. In this e-content, I am going to discuss about dissociation constant. It is defined as the ratio of dissociated ions to the original acid or bases in the solution. For acids, the acid dissociation constant is defined as the ratio of concentration of dissociated ions to the concentration of original acid. Whereas for the basic solutions, the base dissociation constant is defined as the ratio of concentration of dissociated ions to the concentration of original base. For a general acid-base reaction of the type Ha reacting with water in equilibrium produces H3O plus A minus. The dissociation constant can be written as Ka is equal to concentration of H3O plus concentration of A minus divided by concentration of Ha. Dissociation of weak acids. Consider the dissociation of a weak acid Ha in solution. Ha gives H plus A minus. Applying the law of mass action, Ka is equal to concentration of H plus concentration of A minus divided by concentration of Ha, where Ka is the dissociation constant of the acid. If the initial concentration of the acid is C moles per liter and alpha is the degree of dissociation, then Ha gives H plus A minus. So C is the initial concentration where the concentration of products will be 0. After the reaction proceeds, the concentration of the reactant will be C into 1 minus alpha and that of the product will be C alpha, C alpha. The dissociation constant Ka is equal to C alpha into C alpha divided by C into 1 minus alpha, which will be equal to C alpha squared divided by 1 minus alpha. The Ka values for weak acids can be calculated by conductivity measurement of alpha. Alpha is equal to lambda divided by lambda naught, where lambda is the molar conductivity of the solution and lambda naught is the molar conductivity of the solution at infinite dilution. Dissociation constants of some weak acids. Acid and Ka values. For acetic acid, the Ka value is 1.8 into 10 power minus 5. For formic acid, it is 1.77 into 10 power minus 4. For oxalic acid, the Ka value is 1.25 into 10 power minus 2. Dissociation of weak bases. Consider the dissociation of weak base BOH in solution. BOH gives B plus OH minus ions. Applying the law of mass action, Kb is equal to concentration of B plus concentration of OH minus divided by concentration of BOH, where Kb is the dissociation constant of the base. If the initial concentration of the base is C moles per liter and alpha is the degree of dissociation, then BOH gives B plus OH minus. At the beginning of the reaction, the concentration of BOH will be C and the concentration of products will be 0. As the reaction proceeds, the concentration of reactant will be C into 1 minus alpha and concentrations of products will be C alpha and C alpha. The dissociation constant Kb is equal to C alpha multiplied by C alpha divided by C into 1 minus alpha, which will be C alpha squared divided by 1 minus alpha. The Kb values for weak bases can be calculated from alpha by conductivity measurement. Alpha is equal to lambda divided by lambda naught, where lambda is the molar conductivity of the solution and lambda naught is the molar conductivity of the solution at infinite dilution. Dissociation constant of some weak bases. Bases such as ammonia will have the dissociation constant of 1.8 into 10 power minus 5. For methylamine, it is 5 into 10 power minus 4, and for aniline, it is 3.83 into 10 power minus 10. Dissociation of water, that is ionic product of water. Water is dissociated into H plus and OH minus ions. H2O gives H plus plus OH minus. Applying the law of mass action, K is equal to concentration of H plus concentration of OH minus divided by concentration of H2O. Since dissociation takes place to a very small extent, the concentration of water remains almost constant. So K into concentration of H2O is equal to concentration of H plus into concentration of OH minus, or Kw is equal to concentration of H plus into concentration of OH minus, where the value of Kw at 25 degrees centigrade is 1 into 10 power minus 14 moles squared per liter. Since H plus and OH minus ions are furnished by dissociation of water in equal amounts, concentration of H plus, which will be equal to concentration of OH minus, which is equal to root of Kw, is equal to root of 1 into 10 power minus 14 is equal to 1 into 10 power minus 7 mole per liter. When concentration of H plus is greater than 1 into 10 power minus 7, the solution is said to be acidic. For a basic solution, the concentration of OH minus is greater than 1 into 10 power minus 7, or the concentration of H plus will be less than 1 into 10 power minus 7. Ionic products of water vary with temperature. At a temperature of 273 Kelvin, the ionic product of water will be Kw into 10 power 14, which is 0.114. At 283 Kelvin, it is 0.292, and at 308 Kelvin, it is found to be 1.008. Thank you.